as of today or something. I think it was like as of. Yeah, here,
It's still there.
I think it was like you can't download it anymore.
Oh, you can't download the app anymore? Moment of silence for TikToks.
Oh, they're like very.
Julie, what are you gonna do? No TikToks. Okay, so 27. So what we're gonna do here is derive these two really famous formulas, and then once we derive them, we're going to basically be able to use them for the rest of the year. They're kind of like the big kinematics formulas. So first, we've already derived a couple of the really simple ones. Like for example, if there's no acceleration, then you can just say that the displacement is the velocity times time, right? Is everyone okay with that?
Yep.
Or you might just write it like this, like a lot of times I like to write it like this because I say, just assuming you were to start at position 0 and start at time 0, then I can write this. I don't have to write delta. So you get the idea there. And then, so that's just if there's no acceleration. So if you're just moving at constant speed or constant velocity. And then we also know that if the acceleration is not 0, so if there is some acceleration, then we know that we could write velocity equals starting velocity plus acceleration times time. That's a big formula. We also know that this is equivalent to writing the definition of acceleration. Let me just stop here for a sec. Is everyone okay with this and this being pretty much the same thing? You say the same thing. So this one is, what was the acceleration of that particle? We'll take how much did the velocity change divided by how long that took, and that's what acceleration is. This is just a way of saying, if I want a function that tells me the velocity at any given time, if I know the starting velocity and the acceleration, this is the function that does that. So before we move on, so no questions? No? Okay. So the question would be then, well, how do I get displacement then here? What's the formula for displacement? If there's some acceleration happening, how do I figure that out? So the first one here is a particle starts at rest and the acceleration is a over a time period t. So what's the formula for the velocity? Well, it's just that. Now keep in mind that was starting at rest. Is everyone okay with why that? So what's that number if you're starting at rest? 0. So if that's 0, it's just, oh, my velocity is whatever acceleration times time is. Now, let's look at the distance traveled. Well, let's find the distance. Well, what if I graphed the velocity versus time graph? What's my velocity starting at? 0. And then let's say after some time t, so between time 0 and some general time t, what's my final velocity going to be? How do you feel about that? So if I have this acceleration for this much time, then my final velocity is acceleration times time, assuming I started at rest, right? So my curve goes like this. How do I find displacement? Area under the curve. So what you do is you calculate this area. It's a triangle. So my displacement is base times height times a half. So it would be 1/2 times t, that's the base is t, the amount of time that passed, and the height is a times t. And so if we simplify that, 1/2 at squared. All right, before we move on, any questions? So that one's pretty famous in its own right, just because a lot of times your initial velocity is 0. For example, who can name a common scenario that might pop up in a physics question where the initial velocity is 0?
You start at a location, like point A to point B, and like back. But because your point A, your momentum is starting at 0. That'd be a simple example.
I think I agree. I mean, yeah, if I'm having to go from point A to point B and I start at rest, I get in my car, turn the car on, right? I'm initially at rest and I start accelerating. Or another one, here's one. When you drop something, right? And so a lot of times you want to talk about, how long would it take for a baseball to we drop it off a 10-meter building, how long does it take to hit the ground? Well, we can use this kind of equation to analyze that, because when you drop something, the initial velocity is 0. Okay, so good to move on? All right, so 28 is now a car is traveling with some initial velocity v0, and they experience an acceleration a over a time t. So now, so for 28, the only difference between 28 and the last problem is that now there's some initial velocity. Okay. So same analysis pretty much. What's my equation for the, it says particle, that's car, whatever. I guess car can be a particle. So my velocity is v0 plus acceleration times time. Okay, simple enough. Same formula we've been looking at for a couple days now. So there's my formula. He's famous. Now let's look at the graph now, velocity versus time graph. This time though, I don't start at the origin. I start up at some v0. This took some amount of time, t. And then what's my final height here? Anyone out there knows the answer to this one? Pretty close. V0 plus at, very good. How do you feel about that? Okay. So let's find the area. Area time. Okay, so the area, look at that little block down there. How wide is he? How tall is he? His width is t. His height is v0. So v0 times t. Plus, how wide is this triangle? T. How tall is he? AT. Very good. Trying to nice. Because you see how this height is v0, this height is v0 plus AT, so the height is the difference between those. So the height of this triangular section here is, probably would draw it on there. That's the extra speed we gain by accelerating, AT. So what's this term going to be then? it's a triangle, it's going to be 1/2 AT squared. There you go, famous. Very famous formula there. This says that if you know the starting velocity and you know the acceleration and you know how long that process went for, you can plug into this formula and it'll tell you the displacement, how far you traveled. Okay? Okay, so Julie, we're doing one of the problems, right? Because you're ready to like a previous page. Just want to make sure you do. So that was 28, and then 29 just says, let's suppose to now say you start. Hopefully, it makes sense how this is logically building up. If not, then I failed you. I'm sorry. But now, could we write a position function for a particle that starts with some velocity v naught, accelerates with acceleration a, and then, what's the function over time? So this one's actually very simple. Might sound complicated, but there's actually very little we have to do to get this formula, because here's my particle or car or whatever object is moving. Let's say this is a number line here. This is like the x-axis. Let's say he starts at x naught, some position. Okay. And he starts off with a velocity v naught, and his acceleration is a. Don't we already have a formula for the displacement? So who knows the formula then? What's his position function then? No one knows?
Is this the one you just did from coming?
Pretty much. So if you don't know the answer to this, I'll ask you a simpler question. Let's say I started at position 3. Here's me. Say I started at 3, and let's say my displacement was 5. Where would I end up? 8. There you go. So what's the answer to this question?
So you start at x.
I started at x naught. Started at x naught. And what was my displacement?
Plus v. So you're 12.
No, hold on, it's back up. So where you are is where you started plus your displacement. So where did I start at? X naught. Let's add on the displacement now. V naught t plus 1/2 AT squared. So this is the position function for the particle. Again, where I started plus this sum here is the displacement, is how far would it traveled over that time period. Okay. Let me show you a different perspective if that was confusing. So let's say this made sense, but you weren't entirely sure of how are we getting from here to here. Well, if that was the case, I would encourage you to try to spend some time thinking about what displacement means. Because displacement is how far are you from where you started. But so like here, displacement is just where you are now, your x position, minus your starting position, x naught. And so if I just replace the delta x with that in this formula, does this possibly clear it up for anyone? If they're confused, like if I simply take this formula, replace the delta x with x minus x naught, and then just add the x naught over to the right-hand side to get my formula. That one right here. Okay, well, if it doesn't make sense, my recommendation is to spend some time thinking about it. And you can, I'd be glad to meet with you and discuss it if you have further questions. Okay, so let's use this formula now. On 30, 31, 32, etc. Now bear in mind, a lot of these can be solved with some like tricks, but I want you to use the formula just to see how it works. Okay? So this first one, try applying the formula that we just derived to this problem. And see if it works out okay for it, see if it makes sense. And we'll go to the answer. So that's just a diagram of what's happening. When you get your answer, compare it with what would I have gotten if I had applied a trickier approach here. Just wondering, can anyone do this in their head in like very fast?
No.
Without the formula. Come on, so at least I know someone can. What's the average velocity? 60. So what's the answer? So what's the average velocity? How do you know it's 60?
I don't know. It just went out my brain.
Well, because the average of 20 and 100 is 60, right?
Well, that makes sense.
So if my average velocity was 60, well, let's back up. Who's confused about that? That the average velocity is 60. Okay, so the average, average, we've established that if your velocity is increasing linearly, so like if your velocity is going from 20 to 100 in a linear fashion, okay, then the average velocity is going to be the average of your starting and ending velocities. So the average of 20 and 100 is 60. So on this question, because it's a constant acceleration, then you know that the average velocity is 60. And then you can say, well, if I traveled at an average velocity of 60 meters per second over a period of 5 seconds, how far? You would have gone 300 meters. Does that clear up? Does that make sense?
Yeah.
So we know the answer is 300. How does the formula give us the answer? Okay. Because the formula is probably more broadly useful. This formula is applicable to a lot of scenarios with different unknowns. That trick of looking at the average velocity, it only kind of works in particular situations. Like if I know the starting and ending velocities and I know the time, it's quick. It's helpful. So okay, let's apply the formula. So this is going to be a thing, a source of confusion for many physics students is, I've got this page of formulas. I don't know which one to use. Has anyone ever had that in like a different, I guess what other class did you have that in? Maybe chemistry, probably not. Anyway, so in physics, you might have a page of formulas. Have you had that experience?
AP Chem is more like, I have a whole bunch of numbers there and it's a problem. I don't know if they can work out.
There you go, that's kind of the same thing. So I have all these values. How do I use the values? There's 1, 2, 3, 4 values. I could have also been mean and said the car is 400 kilograms. Ooh, extra information. You know, the driver's favorite food is pizza. Extra information. You don't. So what are we looking for? So here's what you do. If you're saying, I have some formulas I've written down. How do I know which one to use? You first ask, what am I looking for? What am I trying to find here? Displacement. That's what I'm searching for. So I look at it and say, which of my formulas tells me about displacement? Now, one of the things that makes this challenging is we have a couple. Can I use this formula? Displacement equals velocity times time. Can I use that? Not really. This is acceleration going on. So we know that that simple formula can only be used if there's no acceleration. So we just derived this formula that the displacement is initial velocity times time plus 1/2 acceleration times time squared. Which of those numbers do we just know immediately? We know V naught is 20. We know T is 5. Now think about the meaning of this number. That number has meaning, right? 100. So someone do me a solid. Tell me what that number means. Hold on, Aiden got the answer.
So far we go.
Yes, we had never sped up. That's how far we would have gone. Okay. Now plus 1/2 acceleration. Okay, I'm gonna go a little blank there. So I don't know acceleration. They didn't tell me. They didn't give that to me directly in the problem. But then that raises the question: can I find the acceleration without creating a whole bunch of extra work for myself? Yeah. What's the definition of acceleration? Change in velocity over how much time it took. So my velocity change was 80 meters per second. It took 5 seconds, 16. Okay, so now I've got 100 plus 8 times 25, right? That's 200. So you get 300 meters. So let's recap this. A question like this, okay? I'm a big fan of this question, okay, because you can solve it 3 different ways very readily. You can solve it using, sorry, I'm not sure if you can see. I just realized you couldn't see this. You could have drawn this graph and just calculated the area. So you could have drawn the graph and been like, oh, let's chop this up. Hey, guess what this area is right here? 100. There's the 100 in the formula. This area here is 200. There's the 200 in the formula. Okay, we could have done it that way. We could have done no graph, and if we were very confident in this trick working, we could have gone, oh, from 20 to 100, the average velocity is 60, like Julia said, 60. 60 times 5 is 300. Or we can just go and say, I know a formula that will tell me the displacement if I have lots of other information. So there's 3 different ways you could have solved it. Any questions going forward? You know, you can tell it's Friday. It's Friday. There's Friday energy in the air. The lethargy is palpable. The lethargy is palpable. I say. Am I right? I believe that.
My dictionary in my head is not very good.
Lethargy is that feel when you eat like 4 Travis Scott burgers.
Kind of had one.
Not to conflate it with being full, but you'd be like kind of tired and lethargic.
I deserved something 2 days ago.
Just the thing that's not.
Do you guys still see there's a show called Family Guy? Is that show still does that exist? You guys know what that is? A lot of that show's not that funny to me, but there's one really funny one where he just picks up a copy of The New Yorker, which is a magazine, and he just looks up, the comic is just this guy sitting in an office chair and he says, I'd be more apathetic if I weren't so lethargic. He gets you that. New Yorker. Okay, number 30. All right.
Yeah.
So 31 is very similar to the last question. Okay, very, very similar. You know the initial velocity, you know the final velocity, you know how long that acceleration took. So again, I want you to try it out with the formula. Same thing with 32. And same thing with 33. So those 3 questions are a good chance for you to practice and make sure you understand what this formula is doing and how to use it correctly. So I'm just gonna leave that as for like a homework for you, okay? Each one should take you a couple minutes, maybe. Big brain time. I want to go over 34. It's a whole page. 34.
That's a big.
Well, it's a big problem. All right. I'd like to give you guys a couple minutes just to think about it. If you feel like you do have the mathematical tools at this point to solve this problem. But I just want you to read through it and think about how you would approach each one. If you feel confident to proceed, go ahead and get some stuff written down. But, it's a projectile shot straight up from ground level, so straight up in the air, with an initial velocity of 30 meters per second. So think about what information have they given you? Initial velocity is 30. They're also giving you initial position, 0, because you're at ground level. Makes sense to call ground 0. Right? What else do we know? Acceleration is? Very good, very good. So in this question, that one sometimes they don't tell you that explicitly, but it's always implied that you're on Earth unless they say otherwise. Well, we'll do some problems later on in the year where it's going to be, imagine you're on a different planet with a different mass and radius, and we'll look at how that looks. But if you're on Earth, right, it's not unique, our 9.8 is not unique, but it's peculiar, at least sort of to Earth, where if you go to the moon, the G value is about 1/6 of that.
So I have that problem.
Yeah, you could jump a lot higher on the moon, yeah. You have the same mass, because if you go to the moon, the same number of atoms, right? But you weigh less. Okay. So anyway, that's because the moon has, if you're wondering, it's because the moon has less mass. That's the main reason. The moon has less mass. It's also smaller, but actually being a smaller planet, size-wise, tends to actually increase. Yeah, so if the moon had the same mass as Earth and was that tiny size, it would be a huge gravitational field. But okay, in any case, Bailey is 100% correct. For this problem, the acceleration value is g, which is negative 9.8. Make sure it's negative because that acceleration tends to push you down. So go ahead and try your best on these. Okay. Okie dokie. I hope you at least had a chance to read through them, kind of mentally, kind of picture what we're doing here. So first, just visually, it would be like, here's the ground. Here's the projectile. It's shot up in the air at 30 meters per second. It goes up, and then comes back down. Okay, so let's just draw the, let's get the position function and the velocity function in the graph. So that's actually kind of quite a bit of stuff all at once, right? So let's do the easy parts first. How about the velocity graph? Okay, so what's going to happen with the velocity graph here? What's the starting velocity? 30. Very good. Now, what happens the moment that cannonball, whatever projectile leaves the ground? What starts happening?
Starts slowing.
Starts slowing down. Okay, and then I'm just gonna draw the whole thing here. Now, why did I include this? It's got to come back down. It's going to come up, positive velocity, and it's going to reach its peak, 0 velocity, and then it's going to start traveling down. So he's traveling up, slowing down, hits his peak here. At this point, when the velocity is 0, that's when he's at his peak. And then he's going to come back down. Okay. Let's write the function. His velocity is his starting velocity. What am I going to put right here? Minus 9.18, right? Every second, he's going to be subtracting 9.8 from his velocity. So there's his velocity function. Okay. By the way, roughly, how long is it going to take for him to hit the peak? About 3 seconds. 3 and change, maybe 3.1, 3.2. Question? Or you just animating? Visualizing. Okay, let's do the position graph. Here's position versus time. Or is X a good letter to use? Probably not. Maybe I'll say height versus time. That makes more sense to me. Or Y, you can use Y. So, start off with a big slope, right? Big positive slope. And then at some time value, we said roughly 3 seconds, he's going to hit his peak. And then he comes back down. There we go. What kind of shape is that?
Negative.
It's a parabola. So let's look at the formula. Using the formula we just derived. Look. Okay, so the formula we just derived would say that H is equal to initial velocity times time plus 1/2 AT squared. But what's true about my A value here? Negative. It's negative, so it's going to be minus. Now what's half of A? 0.9. Go. Cool beans? So that's question A. So we got the position versus time graph, the position function. We got the velocity time graph, the velocity function. And so how do you answer question B? Is B a tough question or an easy question? Yeah, once you know what to do, it's tough if you're just like, well, I don't know what I'm looking at. I don't even speak English. But if you know what it's asking, then you're like, oh, I have a fast function, right? I have a how fast am I going function, right? If I just plug 2 into this, it'll tell me how fast that's going. What's the answer? When you say plug in 2, you get what, 10.4, I think? There we go. Now, how do I know if I'm going up or down? If it's positive, if my V value is positive, I must be going up. If my V value is negative, I must be going down. How about times 5? Plug in 5. And we already established that we hit our peak height at roughly, what time was that again? 3. About 3. It's probably like 3.1, I'm guessing. So from that perspective, clearly anytime before 3.1, we must be going up. Anytime after 3.1, we must be going down. And what else? No, we're almost out of time, right? Okay. So last thing here, guys. How do you figure out when projectile reaches max height. Well, we kind of talked about that, right? This. So you're basically gonna set the velocity to 0, and then you can plug, once you have that t value, that 3.1-ish, how do you know how high the thing was at that time?
You put it in there.
You put it in there.
I got it.
Yeah, this is the how high is the cannonball function. This is the how fast is he going function. This is the how high is he function. So if you have a time value that you're interested in, like 3.1, you can plug that in to the height function, and it'll tell you how high the projectile was. When does he hit the ground? You could set this equal to 0 and solve it. So if you set that equal to 0, here's a little bit of algebra review for you. Set this equal to 0 and factor out the t. And it looks like this. So times 0, that's the trivial answer, right, when the thing started. And then also you can solve this, set that equal to 0 and solve. And you have the other delta v to figure out. End stream. End.